The first speaker is Sam. Sam, what's your last name pronunciation? It's been like
as an American, I pronounce it Witte, which I'm certain is not the correct pronunciation.
Okay.
But you can pronounce it however you want.
That was the question. Okay, I will pronounce as you prefer. So next speaker for today is Sam Witte. He's going to talk about radio lines from Axion dark matter and whatever the forward modeling is, you will describe it. So please, whenever you're ready.
Thank you very much. So this is actually going to be a slightly different style of talk because Josh Foster and I, who's speaking after me, have agreed to do a two-part talk. So this could also be radio lines from Axion dark matter part 1, where we are going to describe a recent search for Axion dark matter in the galactic center that we've been doing by looking for the resonant transitions between axions and radio photons. And it's based on this most recent paper you see with the authors down here in the bottom. So the goal of my part of the talk here is to describe everything that goes into the forward modeling of it, and then Josh will step in and describe the data analysis and the interpretation of the results. So let me start with the basic idea. This is something that's been around for a while, but it really started to gain a lot of traction back in 2018 when there were a couple of papers out, in particular the ones by Ben Safdie and his collaborators, which started to suggest that near future radio telescopes might allow us to indirectly probe the QCD axion. And the idea was that we take the radio telescope and we point in the direction of a neutron star. And if axions comprise dark matter, you expect those axions to fall into the magnetospheres of those neutron stars. And in these environments, you can resonantly generate radio photons with extremely high efficiency. Now, we're choosing to point at neutron stars because they have extremely large magnetic fields and because they have dilute plasmas. The mixing between axions and photons is directly proportional to the magnetic field strength, and the plasma allows for this resonant transition to the photons themselves. Because axion dark matter in the galaxy is extremely non-relativistic, you expect the overall photon spectrum generated from this process to be extremely narrow, meaning you expect something like a spectral line to appear that's roughly speaking centered on the axion mass. So that's nice because it gives us a direct handle on what to actually search for. And it directly, in principle, if we were to observe it, it would directly allow us to infer properties of the axion itself. Okay, so the search that we have recently done was data taken with the Green Bank telescope, which is a 100-meter single dish telescope that's based in the US. It is data that was actually taken with the Breakthrough Listen initiative, which is the initiative started by Stephen Hawking and Yuri Milner back in 2015, where they basically said, we're going to spend $100 million buying a bunch of time on radio telescopes, and we're going to use these radio telescopes to look for extraterrestrials. Now, thankfully for us, they are looking in dense stellar environments like the galactic center, and they are trying to look for very high frequencies, spectral frequency resolution observations, which is perfect for us since we want to look for spectral lines from axions. So in particular, the analysis that we're going to be doing or that we're going to be telling you about is based on a observation taken in the C-band. This is the 4 to 8 gigahertz band. We're talking about observing the inner few parsecs of the galaxy. It's based on about 4.6 hours of on-target observation, and we have an observation strategy that's something like an on-target, off-target, where we point the telescope at the galactic center, we point away, and we look for spectral lines that appear in the galactic center that don't appear on the off source, where we don't expect to see a signal. Now, because we're going to be looking at the galactic center, you don't expect to see a single neutron star within the field of view. In fact, you probably have hundreds of thousands of neutron stars in your field of view. Most of these neutron stars will not allow for resonant axion photon conversion. So in principle, you really expect on the order of, say, 10 to potentially hundreds of neutron stars to generate these individual spectral lines. And these spectral lines are going to undergo plasma broadening, and they're going to be Doppler shifted by the relative motions of the neutron stars. So rather than look for a single spectral line from a single neutron star, what we're going to see is something like a forest of lines, where each line has some individual characteristic width that's unique to that neutron star, and the overall spread or distribution of those lines are set by the velocity distribution of the neutron stars in the galactic center. So something like what I'm showing here. All right, so let's say we want to calculate the radial flux from an individual neutron star. Let's start with the simplest case and ignore the broader population. In order to do this, we need to understand quite a few properties about the neutron star, about the magnetosphere, and about the environment in which it lives. In particular, we need to understand the magnetic field, the rotational period of the neutron star, the relative misalignment angle between the rotational and the magnetic axes, the position of that neutron star in the galaxy, its velocity with respect to the galactic frame, and its mass and its radius. Now, thankfully, these last two parameters have a relatively limited impact on the overall radio signal. So these are something you can fix to some fiducial set of values. But that still leaves us with about 9 set of parameters here, more or less, which we need to Monte Carlo sample over in a broader range of a population. So for the time being, let's just take these to be fixed and let's discuss signals from individual objects. So the first thing you need to do is understand what the axion phase space looks far away from the neutron star. Since we've defined the characteristic position and the velocity of that neutron star in the galaxy, that means we have a relatively good understanding of what the dark matter phase space should be near in the vicinity of that neutron star. So for example, taking an NFW profile that fixes the density, adopting some Maxwellian distribution based on the gravitational potential, tells you what the velocity distribution should look like. And of course, that should be shifted relative to the neutron star frame. From there, we have a relatively simple problem of evolving the gravitational dynamics into the sort of small scale region around the neutron star itself. Nothing too complicated. But once we understand what the phase space distribution of axions looks like near the neutron star, we need to understand where we're able to generate photons. And in particular, this resonance that I mentioned is triggered when the axion mass roughly matches the plasma frequency of the background medium. The plasma frequency being controlled by the charge density, essentially in these regions of the magnetosphere. So that means we need to define a magnetosphere. And as we've heard in Sasha's talk, this is an area of active investigation. It's not something that is perfectly well understood in many aspects, but there are some sort of broad scale features which are generally expected, which you had seen in Sasha's simulations. Namely, you had seen, for example, torus-like features extending around the closed magnetic field lines, and you had seen dome-like features extending above the magnetic poles or magnetic axes of the neutron stars. And you expect this to be radially falling off with some characteristic distance. Typical values of the plasma frequency in neutron stars or active pulsars can range, for example, between, say, 10 to the minus 5 eV, 10 to the minus 4 eV, 10 to the minus 7 eV. So this is sort of coincidentally in the range where you'd expect to have, say, QCD axion dark matter, meaning that we can naturally trigger the resonant transition to radio photons for the masses that we're sort of most interested in. So if I take, for example, the Goldberg-Julian model, then I can define this two-dimensional surface around the neutron star. This is going to define my resonant conversion surface, or the surface at which I'm able to produce these radio photons. And I can take the next step in calculating the actual probability of an axion converting to a photon at this point. Now, in general, we expect this probability to be proportional to the axion photon coupling, the local magnetic field strength, and there's some length scale involved in the game. And this length scale is essentially determining the overall, is dictated essentially by the gradients of the plasma. And it's telling you how quickly the axion and the photon will dephase, or how quickly you're able to turn off the effective mixing between the axion and photon. And for typical pulsars, you expect this length scale to be, say, on the order of hundreds of meters, tens to hundreds of meters. Now, there are two sort of caveats here. The first caveat is that all of these calculations of this conversion probability to date, all of the analytic formalisms, have assumed that photons travel on straight line trajectories over these length scales. Now, as we heard in Sasha's talk, radio photons in the magnetospheres of neutron stars do not undergo straight line trajectories. They are actually extremely strongly influenced by the presence of the plasma gradients. And so you expect these photons to undergo extremely strong refractions and reflections in the plasma. As a brief example, I'm showing here an illustration of a photon trajectory, say on the scale of, say, 500 meters is the box size. That would be sourced deep in the throats of the magnetosphere near the surface of the neutron star. The axion comes in, creates the photon, and you can see already on very, very small length scales that the photon has begun to undergo extremely strong refraction and undergoes this oscillatory feature, which is essentially due to the strong gradients in the throats between the torus and dome-like features. So that tells us immediately that these analytical approximations are probably overestimating the actual true conversion probability. And so as a result, we actually have to work with numerical sort of approximations that attempt to estimate the axion photon dephasing based on the relative refraction, or based on the deviation from straight line trajectories on small scales. There is a second caveat. So let's consider, for example, the small coupling regime, where we can take or assume that the axion photon conversion probability is much, much less than 1. and consider an axion falling into the magnetosphere of a neutron star. As that axion falls in, it's going to cross the conversion surface, which is again defined by the point at which the axion mass matches the plasma frequency. But the axions at this point are only semi-relativistic. So sitting right behind that conversion surface on very, very small distance scales, you're going to expect to have a reflection, a photon reflection surface, which is just the point at which the axion energy would match the plasma frequency. So in the small coupling regime, most axions will just pass through the conversion surface. They will not convert to photons. They will survive, in other words, and they will pass straight through the magnetosphere unimpeded. But every once in a while, you will generate a photon at that conversion surface. It will reflect off the reflection surface, and it will pass back through the conversion surface once more. But since the conversion back to axions, or the conversion between axion and photons, is generically quite small, you can essentially neglect this second crossing by the virtue of the fact that it's small squared. So in that case, we expect the overall photon production rate to be roughly given by the formula which I had previously described. Now, in the large coupling regime, we actually enter an entirely different problem. In this case, our infalling axion is actually expected to convert to a photon with order 1 probability, which immediately reflects off this reflection surface, crosses the secondary conversion surface, and converts back to an axion with an order 1 conversion probability. What that tells us is that if our axion photon coupling is sufficiently large, we actually expect to have an exponential suppression of our photon production rate. The reason being just that we need the photons to survive this second conversion crossing, and that survival probability is going to become exponentially suppressed. So we need to ask ourselves a question about whether or not we're living in the small or large coupling regime. I'm happy to give details after the talk, but since this is a relatively short talk, I'll just sort of jump to the conclusion. And it turns out that for the neutron stars that we're interested here, we expect that transition to regime to live around 10 to the minus 12 inverse GeV. Now, for perspective, this is about 2 orders of magnitude almost below the cast bound. Meaning if we are actually extending the constraints beyond cast, we are certainly living somewhere between the small and large coupling regime. And we have to deal with this adiabatic, essentially, conversion of axions and photons, which leads to an exponential suppression of our flux. Okay, so I told you we had some axion phase space at large distances. We gravitationally infalled it. We computed some conversion probabilities up to some caveats about how to do this. At this point, we have to deal with the photon propagation. And as I've said before, these photons are going to undergo extremely nonlinear trajectories in the magnetosphere. And as they try to escape, some of these photons are going to undergo resonant synchrotron absorption, which is going to suppress the overall flux of photons that we generate. And this is a tricky problem, but it's one that can be addressed with geometric ray tracing methods. So I'm going to show a simulation from one of our recent papers here. You see the conversion surface for a particular neutron star shown in red, white, and blue. You see the torus and dome-like features here, and photons are shown in black. And the color coding of this torus is just intended to represent what the final position of a photon source at the location where a photon source at the location will end up with respect to the larger scale sky. So photons originating from a red region will end up in the North Pole, while photons originating from a blue region will end up at the South Pole. And if you look closely into the throats of some of these trajectories, you can see some of these extremely nonlinear reflections that I was mentioning before. Now, this is just an example using, say, 20 or so trajectories. In reality, we use on the order of, say, 1 to 10 million trajectories. But we can evolve all of these trajectories to large distances, account for all of these effects like absorption. We can then bin these photons in the sky, and we can sample some random viewing angle or some random orientation between the neutron star and Earth. And we can take all of the photons ending up in that pixel and deconstruct and use those to reconstruct a spectrum. And this is just an example of what a spectrum might look like for one randomly selected pixel, where the frequency here is in units of axion mass times 10 to the minus 5. So indeed, we do recover an extremely narrow spectral line for axions at a gigahertz. This amounts to 10 kilohertz widths. And we can actually, quite accurately reconstruct the time dependence of the signal for any given magnetosphere model, as well as any spectral deformities. So this is sort of the end-to-end of how you generate the radial flux from individual neutron stars, assuming, again, you've been given these 9 parameters here, being the magnetic field, the period, the misalignment angle, the 3 vectors of position and velocity with respect to the galaxy. Now we need to actually consider in reality the total evolution or the population synthesis of the larger neutron star population that exists in the galactic center. So you can do this by breaking this up into two parts. You can try to understand the neutron star formation rate on one hand, and on the other hand, you can try to understand the neutron star evolution. And together between two of these, you can then seed the neutron stars, you can evolve those neutron stars, and you can understand what the population looks like today. So if we take a look at sort of the typical life or the normal evolution of a typical pulsar in terms of its magnetic field and spin period, what you expect are that young pulsars are born with relatively small periods and large magnetic fields. Those pulsars will be radiating mission, and as they do so, they're going to begin to spin down. They're going to begin to align. And in other words, the misalignment angle between the magnetic field axis and the rotational axis will decrease. And the magnetic field, which is being supported by currents on the interior part of the neutron star, is going to decay. Those currents are not fully, they have some finite resistivity, and that resistivity will essentially induce some energy dissipation that supports the magnetic field. Eventually, this sort of downward spiral of decreasing period and decreasing magnetic field will push the neutron star below the so-called death line. This is more or less the line that's expected to differentiate neutron stars, which are capable of actively producing charged particles and therefore actively inducing large amounts of luminous emission from those which cannot. So the neutron stars we see are obviously those which have emission, those which are above the death line, and those which are active. But most neutron stars in our population are expected to be below the death line. They're just too faint to be physically observed. Now, in general, we're interested in any neutron star that can convert. And the conversion line, more or less in this plane, looks something like this, where the overall height of this line will change with the frequency that you're observing. But that means in general that we're interested in both active pulsars and dead pulsars. Anything that's dead at higher spin periods and larger magnetic fields will still contribute to our signal, even though we don't necessarily see it. And in general, as a naive rule of thumb, we expect a larger flux for larger periods and larger magnetic fields. So this tells us that we actually have to do a full population synthesis to try to understand both what the active and the dead pulsar distributions look like in these environments. So we do this by essentially taking some initial distribution functions for the magnetic field, the period, and the misalignment angle at birth. We adopt a magneto-rotational evolutional model to evolve the magnetic field, to evolve the period, and to evolve the misalignment angles today. And then we use some relations to estimate the luminosity based on these properties today, and you can fit those to a pulsar catalog. The biggest uncertainty here is entering through these magneto-rotational evolution models, and in particular with respect to the magnetic field decay. This is something that's certainly an active area of research and something an active area of debate. And as a result, we try to develop two different populations, one based on a fast decay model, in which we assume the magnetic fields of neutron stars undergo exponential decay on, say, mega-year timescales, and one which is a slow decay model, which adopts a much more, giga-year to 10 giga-year timescale for the magnetic field decay. These are two extreme examples, which are tended to bracket these uncertainties, but give us a relatively good handle on how impactful this magneto-rotational evolution model is on our net results. So depending on these models, we can try to approach the spatial distributions and the birth rates in very different ways. If we're talking about a fast magnetic field decay model, we expect this population to be dominated by young stars, particular stars that are, say, mega-year to 10 mega-years old, simply because anything that's older than that will have already decayed past that conversion line and will no longer allow for resonant conversion. And in this case, we can actually take a more data-driven approach. We can use recent observations of star formation activity in the inner parsecs of the galaxy to try and reconstruct or estimate the number densities of neutron stars and the spatial distributions of neutron stars. And in particular, we find that these models tend to predict about 1,500 neutron stars with ages less than 30 mega-years in the inner parsec. In the slow magnetic field decay model, you have stars that are both born in these environments, and you have, for example, globular clusters that have been tidally disrupted as they pass through the galactic center. So you have a much more complicated distribution that has to rely inherently on population modeling. But these models typically tend to predict on the order of 300,000 neutron stars in the inner few parsecs, only a small fraction of which actually allow for resonant conversion. So for both of these populations, we can draw samples, we can then run our ray tracer, we can extract the overall flux within a given pixel based on a randomly sampled neutron star Earth orientation. we can then Doppler shift the line by the relative neutron star velocity, and we can stack the samples. And collectively, this generates our forward model or our signature that we're trying to look for. And in general, you expect it to look something like this. This is the flux as a function of frequency for 3 different choices of Axion mass ranging between 4 gigahertz and 8 gigahertz. And you can see a couple of things here. First of all, you can see the appearance of individual extremely bright and thin neutron stars within our field of view. This is one neutron star, which is persistent on all 3 frequencies, and it's a particularly narrow neutron star. This is because the photons that are coming from this neutron star are actually sourced very, very near to the neutron star surface itself. You can also differentiate the effects of the plasma broadening, which is induced from the motion of the photons, the radio photons, through this time-dependent plasma, from the Doppler broadening, which is induced from the relative motions of the neutron stars in the galactic center. And finally, you can look at the disappearance of neutron stars as you increase mass. And this is simply as a consequence of the fact that in order to induce resonant conversion at larger Axion masses, you need larger plasma densities, and these can only be accommodated with more active neutron stars or larger magnetic field neutron stars. So you expect these generically to fall off at larger frequencies. So with that said, I think I will just, I think I'm probably over time, so let me just say a few conclusions. I think the last few years have shown a major developments in the forward modeling of these systems. We're including many effects which were not included previously, and I think this will continue in the following years as a number of groups are actively pursuing this as their primary line of investigation. So I think that this offers a really enormous promise for trying to probe axions in general. So I will let Josh take over, I think, and show you the results and the interpretations.
So there is a question by Sasha. If it's not very urgent, I would let.
I'm happy to answer questions as well. If
no, of course. But like, if let's ask Sasha if it's urgent.
Apart from urgent, I think that if it is, as I think, like related to precisely also the plasma and the stuff, it can be taken now from Sam, right? And then for other stuff, we can wait the end of the talk probably. So probably Sasha can, right? If Sam is okay, can go ahead with the question.
Absolutely.
I mean, yeah, just a very quick question. Like, I mean, most of the slides you showed this disk and dome kind of configuration, which probably applies for like dead neutron stars. I think I asked someone, doing this earlier, but I forgot the answer. Like, why do you specifically take this configuration, but not, stuff is active pair production, lots of particles, etc.
Right. So that's a good question. The treatment of the magnetosphere at this point has been one of the biggest open things that we haven't been able to address in a meaningful manner, I would say. Everyone at this point in time is more or less taking a charge-separated Goldreich-Julian model, which is the disk dome I was just showing. Obviously, that's not exactly what you expect in active pulsars, as you had shown in some of your simulations. We have considered variations of that where we essentially turn off the domes or turn off the disks in order to simulate what would happen, for example, if you had a very, very strong acceleration along the domes, large Lorentz boost, which would suppress the plasma frequency, or if you had electron-ion separated regions rather than electron-positron separated regions. To a large extent, those types of differences don't make an enormously strong impact. We've also had a couple of conversations with, I think, some of your collaborators, both in Princeton and in Columbia. And some of our understandings from those conversations was that the distributions of charges in the closed zones doesn't expect to deviate enormously from the Goldreich-Julian model. And maybe you can correct me if that's an entirely incorrect statement. I would appreciate it. But up to, say, order 1 charge multiplicities, they had told us that these were reasonable estimations in, say, the 10 to 100 kilometer distances from the surface of the neutron star. The final thing I'll say is that I was discussing with Andrei Belobodorov and his group, and they were kind enough to generate a plasma disk frequency distribution from the recent aligned rotator simulation. Yes. And it has been my hope to actually incorporate this directly into our ray tracing to understand what the systematics of this are. But we haven't actually gotten around to it yet. This is certainly the next item on our agenda.
I mean, the polar zone does have very dense plasma, at least at certain latitudes, not on the whole polar cap, but like in this simulation, the ones that are very close to the axis would have high multiplicity. In reality, the simulations model like multiplicity of 10. In reality, this would be 10 to 5. And what's more important, I think, that you mentioned is the synchrotron absorption. which does depend a lot on the density, because the optical depth just scales with, density to, I think, like half or something power. So, and with the distribution of particles. So, like, I think it's a big caveat that needs to be taken sort of carefully about.
Absolutely. I couldn't agree more. And in fact, I was hoping to discuss with you more during the breaks of the workshop, in fact, in order to understand exactly what it needs to be modeled in order to properly treat some of these issues. So,
okay.
Well, we can postpone this discussion at the end of the second talk, I guess. So, Josh, if you can.
Yep. Let me share my slides.
I don't know if we wanna stop and restart the recording if we separate stuff, but